How can we generate random numbers from a multivariate Gaussian distribution? We'll start by generating two-dimensional Gaussian random numbers whose correlation matrix, which is assumed to be known, is the following: 1 row in the first row and row 1 in the second row. We're going to factor this matrix as a product of a lower triangular matrix, which we'll call the Cholesky decomposition of row, times the transpose of that matrix, which will, of course, be upper triangular. Carrying out explicitly the matrix multiplications, we obtain L11 square, L11 times L21. The matrix is symmetric, and then L21 square plus L22 square. We're going to identify the elements of the first and the last matrix in this sequence of equalities. For instance, by identifying the elements in the first row and the first column of these two matrices, we obtain the following equality: L11 square is equal to 1. From this equality, we derive that L11 is equal to 1. Identifying the elements in the first row and second column of both matrices, we obtain the following equality: L11 times L21 is equal to rho. Since L11 is equal to 1, that means that L21 is equal to rho. Finally, identifying the elements in the second row and second column, we obtain the last equality: L21 square plus L22 square is equal to 1, from which we derive that L22 has to be equal to the square root of 1 minus rho square. Now we're going to assume that we have a way to generate random numbers with a normal 0-1 distribution. So we'll generate in independent samplings x1 and x2 and collect them in a vector. So these components are independent. And from this vector, we're going to generate a vector z1, z2, such that the correlation between both components is equal to rho. And we'll do that by multiplying the vector x1, x2 by the Cholesky decomposition of the correlation matrix. Performing the matrix multiplications and using the explicit form of the elements of the Cholesky decomposition, we obtain the following: z1 is simply equal to x1, and it follows a normal 0-1 distribution, and z2 has a correlation with z1 and then a term that is independent. This variable also follows a normal 0-1 distribution, but now there's an explicit correlation between z1 and z2. We will now generate normal random variables in d dimensions. The correlation structure is specified by the correlation matrix rho, which is assumed to be known. What we're going to do is to factor this matrix as a product of the lower triangular matrix L times L transpose. This factorization is called the Cholesky decomposition. The matrix L is lower triangular, so we can write it as follows: Notice that all the elements above the principal diagonal are equal to 0 in this lower triangular matrix. The pseudocode to generate a normal random variable in d dimensions with a correlation rho is as follows. First, we generate a d-dimensional random vector with independent components. Then we carry out the Cholesky decomposition of rho. And finally, we generate the d-dimensional vector z by multiplying the matrix that results from the Cholesky decomposition of rho times x. Now, let's see the random number generator at work. We've generated a sample of size 3000 from a bivariate Gaussian distribution. The PDF of the distribution is depicted on the left-hand side, and the sample points are plotted on top of the contour curve for the PDF. Let's analyze the properties of the random sample. We notice that the density of this cloud of points is larger at the center of the distribution, corresponding to the maximum of the PDF. This density becomes smaller as we go to the tails of the distribution, corresponding again to decreasing values of the PDF as we approach the tails of the distribution. Finally, notice the elliptical symmetry of the cloud of points, which corresponds to the ellipses of the contour plot for the PDF.